Hi everyone, welcome to Accelerated Computing video series. In this module, we are going to cover LLM benchmarking. We are going to go through three main pillars of LLM benchmarking, which includes quality, speed, and cost. We will cover the key metrics that can be used and also the main types of methodologies and strategies that can be used for LLM benchmarking. We are also going to demo two main frameworks which can be used to quickly benchmark and assess LLMs for individual generative AI use cases. So if you're ready, let's start. All right, so let's start with a brief introduction to LLMs, which are the foundation of many AI applications that we use today. LLMs are essentially deep learning algorithms trained on an enormous amount of text data, enabling them to understand and generate text that closely resemble human language. We see LLMs powering everything from chatbots that provide customer support to tools that generate creative content and even those that write code. The LLM landscape is actually incredibly dynamic. New models are being released frequently with names like GPT-4o, Llama 3, Mistral, Cloudy, Free, and Gemini, which are becoming increasingly familiar. These models are constantly pushing the boundaries of what's possible with AI. Now let's move on to the core of our discussion, which is the topic of LLM benchmarking. Benchmarking is crucial in the development and application of LLMs. It provides a structured way to assess how well these models perform and how they stack up against each other. Benchmarking helps determine which model are best suited for a specific task. By identifying strengths and weaknesses, we can focus development effort on areas that need improvement, ultimately leading to better LLMs. To evaluate LLMs comprehensively, we need to consider three main pillars: quality, speed, and cost. So let's start with the first one, which is the quality, which focuses on the accuracy and relevance of the LLM's output. In this pillar, we assess whether the generated text is coherent, factually correct, and addresses the prompt effectively. Speed is another pillar, which is especially important for real-time application use cases such as the chatbot. In this pillar, we measure how fast the model can process information and generate responses. Metrics like inference speed, throughput, and latency come into play in this pillar. The third pillar is cost, which is always a factor, specifically when deploying LLMs at a scale. We need to analyze the cost per token, the cost per GPU usage, and even the overall cost effectiveness of different model and deployment strategies. Now let's go through each of these individual pillars with more details. So we start with the first pillar, which is quality. So let's break down the quality evaluation of LLMs further. We have general benchmarks designed to assess broad language understanding. So that's the first category when we are doing any sort of quality evaluation for LLMs. For instance, we got truthful QA, which focuses on the model's ability to distinguish between facts and misinformation, which is crucial for generating reliable output. We also use task-specific benchmarking that assess a model ability to perform certain tasks. For instance, we got the human eval benchmarking dataset, which is designed to evaluate how well a model can generate code. It presents the model with coding challenges and assess the correctness and also the functionality of the generated code. Similarly, we have another benchmark, which is empty bench, which focuses on the conversation skills, evaluating how well a model can engage in multi-term dialogues, understanding context, and also provide relevant responses, which is very, you can see it a lot in chatbot use cases. In terms of metrics, let's dive in deeper into the quality metrics used to evaluate LLMs. These metrics help us quantify how well a model understand and generate language and how accurately it performs specific tasks. So the first metric is perplexity, which is like a measure of surprise for the model. A lower perplexity score means the model is less surprised by the text it's processing, indicating a better understanding of the language. Another metric is BLUE, which is tailored for machine translation. It compares the model's translation to human references and calculates a score based on the similarity of words and phrases. The higher the BLUE score, the closer the translation is to the human reference. Another metric is MMLU, which is a broader benchmark that tests a model's knowledge and reasoning across various subjects. It's designed to evaluate how well a model can generalize its understanding to different domains and solve diverse problems. Now let's go to the second pillar, which is speed. So speed metrics help us evaluate how quickly an LLM can process input and generate output, which is a crucial factor in determining its real-world usability. Throughput is all about the model processing speed. So we got a metrics such as token per second, which tells us how quickly the model can churn out the text. The higher the TPS, the faster the model that can generate large amount of text, making it suitable for tasks like content creation or larger scale text analysis. Latency, on the other hand, focuses on response time. A key metric here is time to first token, or TTFT, which measures how long it takes to get the very first token of the response. For applications that require snappy interaction like chatbots, a low TTFT is essential. Finally, we have metrics such as percentile latency, things like P50 or P99, which give us a broader picture of response time distribution. P50 is the median latency, meaning half of the responses are faster and half are slower than that P50 number. We also have P99, which focus on the tail end of the distribution, capturing the time within which 99% of requests are completed. This is important for understanding worst-case scenarios and potential performance bottlenecks that might impact user experience. Now, the third pillar, which is cost, which is also an important pillar for benchmarking and LLM assessment. So, the cost metrics, which are associated with the LLMs, there are like a number of different factors with the cost aspect, which understanding the metrics related to the cost is crucial for making informed decision about model selection and deployment and ensuring alignment with the budget constraint that we usually have. So pricing model for LLM inference services can be diverse. A very prevalent approach, particularly for cloud-based API, is serverless API input. In this model, you only pay for what you use, typically priced per token processed. So in this case, you don't need to have an upfront investment or fixed infrastructure costs. However, it's essential to keep the track of the usage pattern to avoid unexpected expenses. Another aspect to consider here is the distinction between input and output token pricing. Input token represent the prompt that you send to the model and generally priced lower than the output token. And also the text, which is that text generated by the model. This difference reflects the computational demand of text generation. To simplify cost comparison across model with varying input and output token pricing, a blend price matrix is often used. This matrix, usually based on the fixed input to output token ratio like 3:1, provides a consolidated cost measures facilitating easier evaluation of the cost effectiveness of the model. So let's just get to this price per token. Let's deep dive in this kind of concept, which is you usually see it a lot when you are using LLM through the API from different providers. So it's very important that we first understand the concept of tokenization. LLMs work with text broken down into the token, which can be whole word or a part of the word. Different models have different tokenization methods, meaning the token count for the same text can vary. This directly affects cost as pricing is based on the number of tokens processed. Calculating cost in per token pricing model is straightforward. Multiply the number of input token and output token by the respective pricing and sum the result. For instance, if input token cost is $10 per million and output token cost $30 per million, a request with 1000 input token and 330 free output token would incur a cost of $0.02. To manage cost effectively in these cases, several strategies can be employed. So prompt engineering focuses on creating clear, concise prompt that convey the necessary information with fewer tokens. So we had like a dedicated a video on how you can do cost optimization through proper prompt engineering, which I add the link in the description of this video. Also, fine-tuning of the model for a specific task can also help to reduce prompt length, further decreasing input token count. However, bear in mind that fine-tuned models might come with higher token pricing. Batch inference, where multiple requests are processed together, can lead to cost saving as well, as some providers offer discount pricing for this approach. However, this might not be ideal for application requiring immediate responses due to the potential increase in processing time. So, beside that per token based pricing model, there are some other factors that impact the pricing and also the total cost of LLMs. So the very first thing is about the model size and the complexity, which play a significant role in the cost of the LLM. Larger model with billions of parameters offer boast impressive capability but demand more computational resources and memory, which leads to higher costs regardless of whether you are using a cloud API or self-hosting. Inference speed, that's another factor, which closely tied to the throughput. And that actually just directly impact the cost efficiency. Faster inference means less time and fewer resources are needed to process a given amount of text, and potentially lowering the cost per unit of output, such as the cost per million of token. Context length also influence cost. Longer context, enabling the model to consider more input information, can increase computational requirement and memory usage, potentially leading to higher expenses. Customization through fine-tuning or other techniques can also improve performance for specific tasks, but sometimes come at a price. Some providers charge higher per token rate for customized model compared to their base counterpart. Finally, deployment options play a crucial role in determining overall cost structure for LLMs. Cloud-based API endpoints offer the flexibility of pay-as-you-go pricing, eliminating the upfront investment and fixed costs. Self-hosting provider provide also more control over the hardware and optimization, but it necessitates managing infrastructure by the organization. Selecting the appropriate deployment strategy depends on factors like usage volume, customization requirement, and technical expertise within the organization. All right, now let's talk about more around like if you want to do self-host. So instead of just using the API to access the model, if an organization want to do self-hosting. So while cloud-based APIs offer convenience, self-hosting LLMs on the infrastructure can provide greater control and potential cost saving, especially for high volume usage or specific customization needs. However, this approach requires technical expertise in infrastructure management. The primary cost driver in self-hosting is GPU rental. Price vary significantly based on the type of GPU, provider, region, and rental duration. Higher end GPU like the A100 and H100 from NVIDIA offer greater performance but come at a premium cost. Beyond GPU rental, you need to consider additional expenses like storage, networking, electricity consumption, and maintenance. These factors can add up, so it's essential to factor them into cost calculation. So through proper cost benchmarking, which is critical to determine the actual cost effectiveness of different GPU configurations and optimization settings. So you need to experiment with various batch size, context length, quantization level, and other parameters to find the most cost efficient setup for your specific workload. So now let's examine the key hardware component and how they influence the model processing speed, which are actually important if you want to do any sort of cost benchmarking. So the very first hardware factor is GPU memory bandwidth, which is especially crucial during the decode phase of LLM inference. This phase involves retrieving large amount of data from memory, and a higher bandwidth allows for a faster data access, leading to increased throughput. So you can imagine a highway with more lanes, more cars can travel simultaneously, resulting in a faster overall traffic flow. We got also GPU processing power measured in flops, which is another determinant of throughput for an LLM. So LLMs usually involve complex mathematical operation, and a more powerful GPUs can handle these calculations faster, particularly during the per-fill phase, which is very compute bound. It's like having a faster engine in a car, which can accelerate more quickly and also reach higher speed. The next elements of the hardware which impact the performance is the HBM, or high bandwidth memory, which is a type of memory specifically designed for high speed data transfer. It's like a superhighway for data, allowing LLMs to access and process information much faster compared to the conventional memory type. Another element is CPU offloading, which is a technique where certain tasks like storing model weights are offloaded to the CPU, which can help to free up precious GPU resources for more demanding operation. This can improve throughput. However, the efficiency of data transfer between the CPU and GPU become a critical factor. If the data transfer is slow, it can negate the benefit of uploading. Another kind of like techniques that can help to improve the performance and also even reduce the cost is quantization, which is more around reducing the precision of the model weight. So from FP, or floating point 32, or floating point 16 to integer 8 or integer 4, which can significantly decrease memory requirement and speed up the computation, leading to higher throughput. However, one thing that you need to consider is that to ensure the quantization does not lead to a significant drop in model accuracy. Caching is another approach that can help. So efficient caching mechanism like KV caching can store frequently accessed data in faster memory, reducing the time spent needed to spend on retrieving and improving the throughput. Batching, which means processing multiple input sequence concurrently through batching, can help, which is through more like a parallel processing capabilities, can increase the overall token processed per unit of time and enhance throughput. However, optimal batch size need to be carefully determined, considering the trade-off between throughput and latency. In terms of model architecture, so improving the efficiency and attention mechanism, for example, through techniques like grouped query attention or flash attention, can reduce memory bandwidth requirement and speed up the decode phase, leading to higher throughput and improving the performance. One thing that also you need to consider is that the fact that beyond hardware, various optimization technique can be applied to enhance LLM throughput, which are through those key techniques that we cover in this slide. All right, now that we have a very good understanding of different pillars of the benchmarking, which are, as we mentioned before, quality, speed, and cost. Um, these are like the key things that you need to use in order to navigate the world of LLMs, which can help you to just make a strategic decision and do more like a kind of cost performance trade-off. The ideal scenario is to identify solutions that deliver the best balance between performance, encompassing both throughput and latency, and also cost. This requires a thorough evaluation of different model provider and hardware configuration, benchmarking, and doing the benchmarking. These benchmarking, which are crucial to compare the cost per million tokens, throughput, latency across various options, allow you to pinpoint the most cost-effective choice aligned with your specific workload and also desired performance level. Also, optimization, as we mentioned before, are crucial in maximizing efficiency. Techniques like quantization, caching, batching, and all those things can be used to improve the potential benefit of LLMs for your use cases. Now let's talk about these like the different types of benchmarking method that you can do. The very first thing is about the performance benchmarking. The key here is to measure the end-to-end performance that user experience in real-world scenarios. This goes beyond theoretical maximums and focuses on the actual speed and responsiveness that user experience. In here, it's crucial to align benchmarks with typical use cases to ensure that reflect how LLMs are used in practice. This customer-centric approach provides a more realistic assessment of LLM performance in various applications. To gain a comprehensive understanding of LLM performance, we subject them to various workload types. One crucial aspect here is this test model with different input-output length. For instance, we might evaluate performance with 100, 1000, or even 10,000 tokens. This variation in token length helps us understand how the model behaves under different demands. It reveals whether the model excels in handling short, concise prompt, or if it maintains efficiency when processing lengthy input and generating extensive output. Moving on to quality benchmarking. So we talked about performance benchmarking. In terms of quality benchmarking, we aim to evaluate the inherent capability of LLMs. To achieve this, we usually employ standardized data set and task. This ensures consistency and allow for objective comparison between different models. Key areas of assessment in here for quality include the reasoning, knowledge, and coding, reflecting the core functionality expected of LLMs that we usually use. These benchmarks help us understand how well LLMs perform in areas crucial for various applications. And the last but not least, which is load scenarios. So we need to consider load scenarios to assess how well LLMs handle concurrency. We compare performance when processing a single prompt versus handling multiple prompts in parallel. This simulates real-world application where LLMs might encounter numerous requests simultaneously. Evaluating performance under these different conditions help determine how effectively the model manages concurrent interaction, reflecting its suitability for high-demand scenarios. All right, so that's all for in terms of like the theory that you need to know when it comes to the LLM benchmark. So we talked about those three key pillars, which is again, it's quality, speed, and cost. We talked about different metrics and different factors that you need to consider, and also some of the benchmarking strategies. In the following part, I'm going to go through and demo kind of like a website that you can use to just, because there are a number of different, I would say, framework that can help you to, even without doing any sort of experimentation, at least shortlist the model that you want to do. So they already done some level of benchmarking, and it's very useful so that you can use those data and accelerate your experimentation. So I'm going to demo some of those frameworks which are popular and that can help you to quickly get a very good understanding and even like shortlist those top LLMs that you want to use in order to run your very custom benchmarking for your use case. All right, now let's quickly go through two key frameworks that I usually use if you want to assess any sort of LLMs. The very first one, let me just close this, is this website artificial analysis. So artificialanalysis.ai, if you go there, and that's actually just, it's become very popular for benchmarking different models across different model providers. And as you can see, it actually just benchmark the model across three main pillars that we discussed: quality, speed, and price. So as an example, you can see different models, and then in terms of like the quality, you can see the O1 is actually just through some benchmarking get a higher score. But then when it comes to the speed, O1 mini is actually leading. Or when it comes to the price, GPT-4o mini is the one that actually just is better compared to the other model. So it's actually a very comprehensive place that you can get result for a lot of different, I would say, models, and or even like on different model providers like AWS, Azure, Google, and some even like third-party model provider. You can just go through and check. You see, like they have like a very detailed benchmarking and result that can help you a lot to identify the models that can help you to address your use cases. The very second one, which is from this Center for Research on Foundation Model, I think it's from Stanford University. And this one is also have like a leaderboard that you can just go. You see, like these are like a number of different benchmarking that you have, and then you can just, let's say, for this specific one, you can just go and identify which model actually for that specific kind of benchmarking is leading. Like here is like Cloudy 3.5 Sonnet. And also if you go to the model section, you have all these different models, the description, and even there is like a proper scenario based kind of like a comparison that you can, based on your use cases, you can identify which scenario is more relevant, and then find out like how that specific model are just operating against those benchmarking scenarios. These are like the two key frameworks that I usually use to get some initial understanding of the performance, quality, and also the costing of the model. And then I use this and then shortlist like, let's say, 5 to 10 models that can help me, and then I started to experience with those to identify which one is actually just the most suitable option for running any specific generative AI use case.